Billions of years ago, our nearest planetary neighbor, Venus, may have had oceans and rivers, life-giving habitats like the ones that grace the early Earth. Today, its burned-out surface is a global fossil of volcanic destruction. Concealed beneath a dense, toxic atmosphere. Scientists are now unveiling daring new strategies to explore its tortured landscapes, to search for clues from a time when the planet was alive. How did Venus descend into this hellish state? And how did our planet, Earth, manage to survive? At the surface, the air is 95% carbon dioxide. So dense, it's more like an ocean than an atmosphere. And it's hot enough to melt lead. Overhead, thick clouds of sulfuric acid. No spacecraft has lasted longer than 2 hours on Venus. All we have seen close up, a few images transmitted by the Soviet Venera landers back in the 1970s. Radar images from the Magellan mission in the 90s have stoked our desire for more.
We think of it as this sort of ugly, forbidding, scary place because we've seen these few Russian lander images of these sort of eroded rocks and, crushing atmosphere. But when you look at the Magellan imagery and you see this bewildering array of volcanic forms and flows and bizarre and interesting canyons and valleys and channels that have been carved by liquid lava and volcanoes of different sizes and shapes, I think the surface of Venus is probably really beautiful.
Thousands of years ago, Asian skywatchers saw Venus as two separate stars. Qiming, the beginner of brightness in the morning, and Sangyang, the exalted western one, in the evening.
It's always sort of flirting with the edges of night. You'll never see Venus at midnight up high in the sky. It's always just in the edges of dawn and dusk.
Sumerian priests saw it as one, Inanna, goddess of sex, fertility, physical beauty, and attraction. Inanna became Aphrodite to the Greeks, born from the foam of the sea, protector of those who sail. The Hellenic goddess of love beckoned us to venture into the unknown. Roman leaders declared April the month of Venus throughout the empire. During the festival of Veneralia, Romans honored purity and piety in affairs of the heart. Across the Atlantic, Venus was seen as the little brother of the sun.
In a way, the most astute Venus observers were the Mesoamericans, the Aztecs, the Maya, the Toltecs. For those cultures, Venus was this male, macho warrior with a spear going down into the underworld and doing battle against the enemies of humanity. We think of Venus as Botticelli's Venus, the feminine figure in our culture, but it's around the world, Venus has had a lot of very different manifestations.
In time, the Venus of myth gave way to the scrutiny of science. In 1610, Galileo Galilei observed crescent Venus changing through phases, like the moon. Yet another clue that planets orbit the sun. But even through his telescope, Galileo could not discern its features. Finally, in May 1761, thanks to a rare alignment, the Russian astronomer Mikhail Lomonosov glimpsed its distinctive character.
About once every 100 years or so, Venus actually passes in between the sun and the Earth, and you can see the little dot of Venus moving across the face of the sun. At the moment when the dot of Venus starts to cross the disk of the sun, the very first moment and the very last moment when the dot of Venus moves off the disk of the sun, something weird happens. There's a distortion, what is called the black drop. It's almost like the edge of the sun kind of leaps off towards it and then is distorted inwards. And Lomonosov realized that that would make sense if Venus had an atmosphere. Once you know that, then you can deduce the diameter of Venus, and they said, oh wow, it's basically the same size as Earth. It's the size of Earth, and yet it's so bright. Why is it so bright? Oh, because it must be covered in clouds. And they were right about that as well. And the assumption at that time, which was reasonable, was that the clouds are made out of water.
The idea that Venus was like Earth sparked the imaginations of fantasy and science fiction writers.
I remember seeing a book when I was a kid that said that Venus might have prehistoric jungles and dinosaur-type animals. I thought that would be really exciting, but turned out to be nothing like that.
At the dawn of the space age, Mariner 2 was the first successful mission to another planet.
Way back in 1962, Mariner 2 became the first spacecraft to explore Venus on a flyby, and it made a fantastic discovery that the Venus surface was very hot. Unfortunately, that was not very good for Venus exploration because all the classical ideas about Venus being habitable with people and forests living on the surface just went out the door.
Stranger still, NASA's Mariner 2 found that the planet rotates very slowly and backwards compared to Earth. Americans celebrated the triumph. Not to be outdone, the Soviet Union attempted at least 16 missions to Venus between 1961 and 1984. December 1970, Venera 7 made the first successful landing and the first transmission of data from its surface. Nearly 5 years later, Venera 9 and Venera 10 captured the first images of Venus's tormented landscape. In December 1978, the American Pioneer Venus orbiter began a 13-year radar mapping mission. It was followed by a separate Pioneer multiprobe dropped into the atmosphere.
Atlantis, Houston, Sunnyvale had a good direct check and their command is complete.
And a decade later, NASA's flagship Magellan was deployed from the Space Shuttle on an unusually long 15-month journey inward to Venus.
Okay, Peter, we copy. Pick up.
Looping pole to pole more than 4,000 times, Magellan's imaging radar mapped more than 97% of Venus's landforms. Among Magellan's findings, the volcanic surface of Venus overlies a surprisingly thick crust. Remarkably, about 3 billion years ago, Venus was probably much more like Earth. Each one nurtured the promise of life.
They're the same size, they formed in roughly the same place. There's a lot of circumstantial evidence that Venus had a more Earth-like environment when it was young, so they may have both had warm oceans and all the other conditions necessary for an origin of life at the time when Earth apparently had an origin of life.
Our biggest problem with Venus is that we have so little information about its ancient past. The surface of a planet, and to some extent the atmosphere of a planet, are like a crime scene. Venus is the worst crime scene imaginable because it's been almost completely disrupted over time. And the big question for those of us who are trying to study Venus and understand its history is, when did Venus's evolution really diverge from Earth's evolution?
Venus and Earth are the twin planets. It's the only planet that is likely to be still geologically active in some of the same ways as the Earth. It's really a huge laboratory for understanding the Earth because of its many similarities as well as some differences.
So Venus is kind of the Earth's evil twin sister. It shows how two worlds of similar size, similar density, not that far apart in terms of distance to the Sun, evolved very differently.
Early on, Venus was on a path similar to its sister planet Earth. The radar data hold intriguing clues to a watery past, including vast plateaus made up of granite rocks that likely formed at the bottom of an ocean.
There are areas on Venus that look like continents. They're high standing, they're kind of wrinkly. They are also the oldest rocks on Venus because Venus has had this weird history where much of the surface is new. So these rocks are the only rocks from the first 80% of the history of Venus. That's where we want to go. That's where I want to go, is to these areas which are called tessera terrain because of their tile-like appearance. Whatever it is that spurred the formation of life, in my mind, why wouldn't it have happened everywhere? And that's the record that we're looking for in the rocks of the tessera. Were there evidence of ancient environments that would support life?
Venus is close to Earth in size, mass, and rocky composition. But that's where the similarities end.
Now, one thing we've learned in general about the formation of the planets is that the final stages of planetary formation were characterized by a small number of really huge collisions. Those last few violent collisions happened on Earth in just such a way as to leave it with a moon, and on Venus, through a different combination of impact size and impact angles, it may have been left with no moon, but with its very slow rotation.
Compared to our 24-hour day, it takes more than 243 Earth days for Venus to rotate just once, the longest day in the solar system.
And it rotates in the opposite direction, so that if you were on the surface of Venus and could see the sun, it would rise in the west and set in the east. You know, on Earth, the sun moves along in the sunrise at hundreds of miles per hour. So you have to be up in a jet airplane if you want the sunset to last forever. On Venus, though, it's 4 or 5 miles per hour. So you could kind of walk along at a good clip and keep the sunset going or the sunrise going as long as you wanted. The pace of the planetary rotation is a human walking pace.
Even that slow pace may be winding down.
The very thick atmosphere of Venus is actually being pushed and pushing back from the topography and changing its rotation rate very slowly and very slightly over the decades. And that has been measured by ground-based units and by Magellan and even by Venus Express, the most recent European mission.
Though the surface creeps along without hurry, the clouds move quickly, and their speeds change. The Japanese Akatsuki probe, also known as the Venus Climate Orbiter, recently found that the atmosphere spins much faster than the planet itself, a phenomenon called superrotation. This movement is driven by heat rising continually from the surface. Mysteriously, the planet lacks a key feature that protects Earth and its atmosphere: a strong magnetic field. Without this protective shield, intense ultraviolet rays from the sun split water molecules apart in the high atmosphere. Then the sun's intense stream of charged particles, the solar wind, carries much of the hydrogen away into space.
In the very early solar system, when the sun was not quite as bright as it was now, Venus was much more habitable. But just a little bit of increase in solar brightness kicked off a runaway greenhouse effect, where the oceans evaporated, put water vapor into the atmosphere that increased the greenhouse, and it ran away to become the very hot, very dry planet we see today.
We definitely believe that Venus had much more water at the surface than it does today, potentially a shallow ocean's worth of water. We really have no information about when that water was lost.
That water could have persisted for billions of years. Billions. And on Earth, life evolved incredibly quickly, actually, considering the meteorites that were hitting the Earth. So why not Venus? And if the answer is it didn't happen on Venus, that tells us something too.
As Venus lost its water, its atmosphere gave way to the noxious outpourings of volcanoes, the primary source of carbon dioxide. But Venus lost its ability to recapture that carbon, trapping itself in a terrifying loop.
Ultimately, the oceans boiled off, partly because of the greenhouse property of water vapor itself, leading to this positive feedback where the more water that evaporates, the more the planet heats up because of the greenhouse effect of the water vapor. And then once the oceans boil off and Venus loses its oceans, then that destroys the carbon cycle, because you still have CO2 coming out of volcanoes on Venus, but there's no way to remove that CO2. The sink disappeared when the water disappeared. And then the thermostat sort of gets pegged in the red zone because you're just adding more and more CO2 to the atmosphere from volcanoes, and it can't lose it anymore without that mediating effect of water, and it ends up in that runaway greenhouse state.
Why did volcanic CO2 run away on Venus, while Earth kept it at trace levels? One reason is a basic difference in the geology of the two planets. Earth, like Venus, harbors a core of molten iron. Over time, the radioactive decay of uranium, thorium, and potassium generates heat. Hot liquid rock punches through where Earth's crust is thinnest, in the middle of oceans, and floods the seafloor with lava. In a process called plate tectonics, growing undersea mountains push aside raft-like sections of the crust, the plates. When they collide with thicker continental crust, they can dive beneath them. As they do, grinding friction causes rocks to melt, hastened by oceanic water, forming reservoirs of magma. The pressure increases until finally a volcano erupts. Plate tectonics generates up to 80 volcanic eruptions each year. Sometimes, this process can release energy on such a large scale that it changes the course of Earth's history. Today, Yellowstone National Park in North America is an open laboratory of Earth's remarkable geology. The rich mix of organic chemicals and geothermal energy in places like this may have given rise to living organisms billions of years ago. The hot springs and geysers we come here to admire are fueled by a dome of magma that is building deep below ground. At intervals of roughly every 600,000 years, this dome pushes the land up into a broad plateau. Inevitably, hot gas and lava explode through the cracks in the land. The plateau suddenly and violently collapses, triggering eruptions so large they blanket the continent with ash.
Plate tectonics is really what makes Earth tick. Plate tectonics is the sort of overall organizing principle almost of Earth's behavior, not just the obvious continental drift and the movement of the continents, but even the carbon cycle and the climate cycle and all of these other aspects of Earth that have to do with the way things cycle between the interior and the surface come down to plate tectonics, and Venus doesn't have plate tectonics.
You can see why by cutting into the crust of these sister planets. Earth has only about 8 kilometers of hard crust under the oceans and no more than 30 kilometers under land. But the skin of Venus is about twice as thick, acting as a rigid lid, locking the surface in place.
If Earth did not have volatile cycling throughout most of its history, and we had a stagnant plate mode like we have on Venus today, then all of the nitrogen and all the carbon dioxide that we see in Venus's atmosphere would be in our atmosphere in the same way.
The dense shell of Venus may never have separated into continental plates, but the heat must still find a way out.
Venus is a really volcanic planet. Most of the surface of Venus is actually covered by volcanoes and several different types of volcanoes.
From the smallest things that we can measure in the radar data, which is about 100 meters per pixel, to huge lava flows, just lava flows that stretch for thousands of kilometers.
The Magellan mission documented a zoo of volcano types.
Venus has some shield volcanoes. Shield volcanoes have low slopes and they look like warrior shields laid on the ground. That's where the name came from. In fact, it came from Iceland. Venus also has several other types of volcanoes that we don't see in other places in the solar system. For example, one very unusual type are some domes that we call pancake domes. And that's because they really look like pancakes. They are flat on top, they have steep sides. Some of these domes have some fractured and jagged edges, and they are known as ticks because they look like squashed bugs. Arachnoids because they have a fracture pattern similar to a spider's web with some concentric fractures and some radial fractures.
The enormous volcanic features called coronae hint that Venus may be subducting rocks back into its interior after all.
Corona on Venus, in a way similar to calderas on Earth where you have a pattern of concentric fractures. There is a collapse or successive collapses.
A plume of hot stuff comes up, pushes up the surface, breaks the surface, and a bunch of volcanism forms at the surface, much like what we see at Hawaii.
The two volcanoes that built the Big Island are, together, about 150 kilometers across. But a few of the coronae on Venus have grown much larger.
There are a couple of very big features. One is 2,600 kilometers across.
On Venus, where we don't see evidence of plate tectonics, volcanoes are really the primary way that we believe Venus is trying to lose its heat or has lost its heat. And so that record that we see of volcanism on the surface is essentially telling us how Venus is trying to cool off, how its interior is losing heat and moving that hot magma and hot lava onto the surface.
About 500 million years to 1 billion years or so ago, something catastrophic happened. When you look at Venus's surface from satellites and you count the craters that you see on the surface, we find out that the vast majority of Venus's surface is geologically very young.
500 million years ago, Venus had cause to erupt volcanoes over its entire surface, its entire Earth-sized surface. And we're still trying to figure out how that happened and why.
With its steadily declining stores of water, lack of magnetic field, no plate tectonics to drag carbon down into its crust, but hordes of volcanoes blasting CO2 into its skies, Venus sentenced its surface to climatic death. A planet turned inside out. Meanwhile, its sister planet Earth managed to survive, to nurture a complex and evolving biosphere. The contrasting stories of Earth and Venus are central to one of the greatest quests in science today: the search for solar systems and life-bearing worlds out in the galaxy. That search, conducted by a growing array of ground and space-based observatories, has so far turned up over 4,000 planets, with thousands more detected but not yet confirmed. Increasing numbers of these exoplanets are close in size to Earth and Venus, with orbits within the habitable zones of their solar systems, where water can exist in all three states: liquid, ice, and steam. Statistical studies indicate there could be billions of them tucked into the nooks and crannies of our galaxy. Is life, even intelligent life, a natural product of the laws of nature? Or is it a fluke? Its chances mostly killed off by all that can go wrong with planetary evolution. So far, Venus has not told us all it can about these questions.
For years and years after we began to really understand Venus, all of the scientists and the space advocates were saying, oh no, Venus is the one place we don't want to go to because it's so hot on the surface. It's hot enough to melt lead. But it turns out that, like Earth, as you get higher in the atmosphere, the temperature gets cooler, and there's a region where Venus is very, very much like the conditions at the sea level on Earth.
The presence of hospitable conditions in Venus's upper atmosphere led to one of the most innovative mission ideas on the books. Imagine an entry vehicle penetrating the outermost layers of Venus's atmosphere. Instead of continuing to the surface, it deploys an inflating envelope, an airship up to 130 meters in length. This platform, called the High Altitude Venus Operational Concept, HAVOC, would host a series of experiments and sensors. At its most far-ranging, it's the start of a permanent human outpost. A science city built in the clouds of Venus. The concept takes advantage of the unique profile of Venus's atmosphere. At ground level, the pressure is like being 900 meters deep in Earth's oceans. It's hotter than anywhere else in the solar system except the Sun. But 50 kilometers up, among the clouds, the pressure has dropped to that of sea level on Earth. It's no warmer than a day in June in Europe or the US. That's where balloon-borne habitats could perpetually float. Consider a crew of scientist astronauts aboard an airship, making their way through the sulfuric acid clouds. Their ship's electric motors, powered by the sun. On their way home from a survey mission.
The nice thing about the balloons in the atmosphere of Venus, if they're very, very large, is that they'd be running with the inside pressure about the same as the outside pressure. It wouldn't burst like a balloon in a catastrophic failure.
These sequences show a well-developed version of a Venus cloud city. The construction of stations this large and complex depends on our ability to harvest materials, like carbon fiber, directly from the atmosphere. Its core mission, to serve as a field station for deploying research probes around the planet and down to its hostile terrain. From their floating platforms, These experimenters would investigate the deep history of Venus's surface and how land and atmosphere connect. They would check for signatures of live volcanoes and the interaction of the atmosphere's physical, chemical, and possibly biological components. All in a quest to discover what went so terribly wrong on Venus. Soviet researchers first demonstrated balloon science with the 1985 Vega 2 probe, riding turbulent hurricane-force thermal currents at 240 kilometers per hour. Vega 2's 3.5-meter diameter balloon found a stable altitude at about 54 kilometers in the most active of the planet's 3 cloud layers. It traveled more than 7,400 kilometers around to the day side of Venus. Vega 2's descendants may deploy from airships to sample specific altitudes. Triangulating their positions, they could form a global sensor network to pick up signs of seismic activity.
So our balloon can listen for earthquakes as it floats around Venus, taking advantage of the fact that the Venus atmosphere is so thick that sound waves from earthquakes will propagate up through the atmosphere and can be measured from balloon or from orbit. It's astounding.
Though it may appear as a featureless planet-wide cloud bank, Venus's atmosphere has its own complex stories to tell.
One of the most important things in the atmosphere of Venus that we need is to understand some of the molecular fossils that are left in Venus's atmosphere. The noble gases of argon, neon, xenon, krypton, those gases that don't react with anything else. They've been in the atmosphere since Venus formed, since the atmosphere formed, and if we can measure those, they provide us these fossil evidence of what that original atmosphere on Venus looked like.
A profile of the early atmosphere would tell us whether Venus once held lakes and rivers on its surface. If humans do someday visit the acidic clouds of Venus, they may find, strictly speaking, that they're not alone. For more than 100 years, astronomers on Earth have noticed enigmatic dark patches that appear only at ultraviolet wavelengths.
My Venus atmosphere friends talk about the fact that there is a signature in the atmosphere that they can't explain. And there is something in the clouds that absorbs UV radiation, and they don't know what it is. That signature may be due to absorption by biota, by cloud creatures.
There are nutrients, there's liquid, there are a lot of the elements that we think of being requirements for life. The one impediment to life may be the strong acid in the clouds. But we've learned more recently of all these extremophile organisms on Earth, including what we call acidophilic organisms, or organisms that love living in strong acid.
There are bacteria on Earth, the Thiobacillus ferrooxidans, for example, which have an absorption spectrum which is very similar to what we see on Venus.
Could life have developed and migrated upward as the surface became lethal? In Earth's atmosphere, microbes have been found at altitudes up to 40 kilometers.
Earth has had 4 billion years for life to fill every ecological niche possible. And we find life everywhere we go. We dig deep wells, we find life down there. We find life in the clouds.
If we have the opportunity to go to Venus and float in the Venus clouds, we should at least think about if we can measure the conditions that might be reasonable for life today, and also any signature of life in the clouds of Venus today.
Though the cloud tops may be temperate, the hot surface is merciless. Venus engineers must take a mechanical approach because even the most robust electronics developed for the military stop working at about 125 degrees Celsius.
Let me show you something. So this is a clock that is fully made out of stainless steel. It's been baked out at 460 degrees Celsius and has been operated in an oven. And our goal with this was to start to understand what are the challenges when you build mechanisms to operate in Venus conditions. First of all, the spring material was really important. We have a clock spring here, as well as also a balance spring right here that is built out of Inconel. Even when you're going to extreme temperatures like Venus, 462 degrees Celsius, the entire assembly would just expand and contract together and you wouldn't get jamming. And we were able to demonstrate and show that by operating this clock.
As on Mars, exploring the surface of Venus will require mobility. But strategies that work for other worlds don't work on Venus. Not even solar power.
Venus does have some solar power on the surface, although it's a fraction of what is available here on Earth is actually available on the surface of Venus due to the thick cloud layers, due to also the red shifting of the light, and that solar panels don't work as efficiently. The other big challenge with using solar on Venus is that Venus has a very long night, about 60 days. Therefore, one of the places we're looking to get energy is from the wind. The idea is you have low-speed, high-density wind coming at you, collect that with a wind turbine, and then directly transfer that to the wheels to drive you at low speed, high torque. You want to directly use that wind energy to move yourself mechanically around the surface of Venus.
We have the sensors on the surface. We have the radio on the surface, but most of the processing power, most of the computers, most of the things that run the mission would be high overhead. We could either put them perhaps in an airplane, flying 50 kilometers above, or maybe in a satellite. The winds of Venus are pretty ferocious. The winds of Venus are going 100 meters per second. Well, one thing we could do is just fly around and let the wind take us where the wind takes us. As long as we can fly faster than that wind, so we can stay in the sunlight.
Venus's extreme surface heat drives a blustery atmosphere of toxic acid rain. But the planet lies within what astronomers would think of as the habitable zone.
Venus is a really interesting case because it forces us to think of where is the inner edge of the habitable zone. Presumably now in our solar system it's somewhere between Earth and Venus. And yet there was a time earlier in the life of our solar system when Venus was within the habitable zone, when there probably was an ocean on Venus.
Mars, we think, at some point used to have more atmosphere and was potentially warmer and wetter. And Venus probably had less atmosphere at some point in the past and had significantly more water than we see today, which today it seems very, very dry. And so it's possible when Venus did have less atmosphere, it was habitable. When it had more water available and less atmosphere, we very definitely think that it has changed over time.
Looking out in our Milky Way galaxy, astronomers are seeking a broader understanding of how planets form and what conditions can nurture an Earth-like world. All other exoplanets lie too far away for us to know much about them. But Venus is giving scientists a chance to understand the alien planet next door.
There's probably millions, likely billions of planets that are like Earth and like Venus. And we'd like to understand what made the one turn into a hot desert. And Earth, on the other hand, turn into a planet with liquid water and habitable for life.
Different aspects of Venus's evolutionary history would put it into the habitable zone, then that tells the exoplanet astronomers that they should not just discard these worlds as hot, inhospitable planets, and that they should go take a look at them. And that would expand the idea of the habitable zone to much closer reaches to the star than we would otherwise think.
When we look out in the galaxy and we see all these Earth-like planets, we're looking for another Earth, right? We're looking for another place that is like our own. We're looking at Earth-sized planets, and the closest Earth-sized planet happens to be the closest planet to Earth. It's Venus. It's right there. So it tells us about how Earth-sized planets form and whether or not they're habitable.
Two planets, born together, nearly the same size and mass, built of the same stuff. At the start of their lives, each harbored oceans and atmospheres laden with water vapor. Over time, one increasingly draped itself in the greens and blues of life. While the other became enshrouded in a toxic haze. Its surface paved over with volcanic outpourings. Which type of world is most common in the cosmos?
We know a lot about Mars. We've sent a dozen probes to Mars. We've sent rovers across the surface. But Venus, we have very little knowledge of. So we need to start learning how to go to Venus. Learn about the circulation of Venus. Learn about the climate. Learn about the weather. Venus needs to be not the forgotten planet of the solar system. If we understand Venus, we learn about the Earth.
I imagine imaged with the right kind of, whatever drone or spacecraft or even humans ultimately going there in very well protected suits. When we get to see it in the right way, we're going to be like, wow, nobody told us. This place is beautiful. And it's massive. Remember, there's much more land area on Venus than there is on Earth, since Earth is 2/3 ocean. And it's going to be just a thrilling place to explore fully when we get the opportunity.